All right, Pre-Calc, we have made it to the last chapter of new material here. So we're in chapter 10, the last one of new stuff. Starting out here, 10.1a on sequences. So we're going to just kind of look at different types of sequences and do some work with those. All right, what is a sequence first? Sequence is a ordered list of numbers, and we call these numbers terms. So some just terminology and stuff first to get through it. If it's a finite sequence has a finite number of terms. So it has a limit to the number of terms. So like 1, 3, 5, 7, 9, 11, if it ended there, it'd be finite. Where you have an infinite sequence has an infinite amount of terms. So in this case, like 1, 3, 5, 7, these dots here, these represent that this thing goes on and on forever towards infinity. All right. Continuing on, some sequence properties. Each term of a sequence is a function of its position. Okay, just some things to think about here. And then once you see them, when we get working, you'll understand it a little better. So there's a lot of wording here. It might be easier just seeing examples. So an infinite sequence is a function whose domain is a set of natural numbers and can be written as a type of sequential formula here where you have like F1 is A1, the next function would be A2, A3, and so on, where you have this AN where that denote A, so then denotes the nth term. So we could pick like any number and put it in for n, and it should be able to work as the function. If the domain of the function is only the first n natural numbers, right? If we have a set limit on it, then we would call it a finite sequence. Okay. An explicit rule or explicit formula. This is a quote unquote rule that gives the nth term so then as a function of n. So just kind of telling you why that could work out for the above wording there, why it's just kind of an unwritten rule that a of n is a function of n. All right, and then a recursive formula. This is kind of another quote-unquote rule that is defining the nth term of a sequence given one or more of the first few terms. So if we're giving a couple terms of the first few terms, and then we can kind of define the terms of n using those previous terms, okay? So if we're given a few numbers early, we can kind of figure out what the nth term is. It's basically what that's saying, okay? So a lot of little gibberish here, and it's a lot of jargon and math jargon in the words here leading up to the examples. But once we get the examples, I think you'll find it's not that bad. All right, so how to use a recursive formula. First thing we want to do is we're going to find all the terms that lead up to the term that we're trying to determine. So if we're trying to determine the nth term, like in the example above, then we want to find out what are the first ones. So in this case, if we're finding the seventh term, we want to find A1 through A6 first, okay? Then because of that, we can kind of substitute whatever the A1 value is in for A2 minus 1. So that would be that. And then we could simplify that answer and then continue those steps until the final term is found. So again, a lot of math jargon there. And sometimes the A1s, the A6 don't help us as much in the nth term. Once we start doing examples, you'll kind of get the idea. All right, so first one's pretty simple here. Let's just look at finding the first four examples, or the next four terms of a sequence to try to find out what's happening here in these sequences. So this first one here, 32, 16, 8, and 4. So we can kind of see that these are being divided by 2, right? You can see every term is being divided by 2. So the next 4 then would be 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. And then 1/2 divided by 2 would be 1/4. So just finding the next 4. So sometimes it's pretty easy. Other times it's a little harder to find out the pattern. So if we take a look at 1B, we got 1 to 2 to 4 to 7 to 11, 16. So you just kind of try to see what we've got here. Well, if we look at this, we've got 1, if we add 1 here, but then we go up 2, to get here. Then we go up 3, and you're starting to see the pattern develop that we go up 4, up 5, up 6. So that would mean that I would have to add 7 to this term to get my next one of 29. Then I would plus 8 to get 37. Then plus 9 to get 46. And then 56 to be my last term there. Okay. So now we want the next one. 1C says find the first 4 terms of the sequence E given by a sub n equals n cubed minus 10. So we just want the first 4 terms. So in this case, I'm just going to go a sub 1, right? We want the first term. So we're basically subbing in 1 for n. So it'd be 1 cubed minus 10. So 1 cubed is 1 minus 10 would be negative 9. Look at the next one, a sub 2. So in this case, I'm going 2 cubed minus 10, which then would be 8 minus 10, which is negative 2. Third term here, we would go 3 cubed, substituting that in for n. 3 cubed minus 10, well, that would be 27 minus 10 is 17. And then the fourth term here would be 4 cubed minus 10. So 4 cubed is 64 minus 10 would be 54. Okay, so continuing on here. So now we want the 6th term in the sequence. So here's where we're going to use that recursive formula. We're going to find all terms leading up to it, and then we can find that last one. So they give us that A1 is equal to 3, and then they give us the formula here. Here's A1 equal to 3, and then they give us this formula here. And they just kind of give us a limitation that n has got to be greater than or equal to 2. So as we go on here, so our first one, if we find that first term, so here's what we kind of use that recursive. We're going to find all the terms leading up to that and then substitute certain values in. So I know already that was given to us right here that A1 is equal to 3. So then if I try to find A2, okay, well, I know my formula is negative 2a, and then 2 my n minus 1, so it'd be 2 minus 1. Okay, well, we know what that is, right? So we got negative 2, because 2 minus 1 is 1. That's a sub 1 would be here. So I can go negative 2 times 3, which I know is negative 6. Okay, so continuing on to the next term, a sub 3. So now, again, same formula, negative 2 to the a3 minus 1. Okay, so that's going to be negative 2 times negative 6, because 3 minus 1 is 2. A sub 2 is negative 6. So it's going to give us positive 12. All right, if we keep going here, a sub 4, negative 2, and then it'd be a4 minus 1. So it'd be negative 2, basically times the term above it, gives us negative 24. So you're kind of starting to see that with these terms, it's then we're basically multiplying negative 2 by the previous term. That's kind of what this is saying right here, is that we're multiplying negative 2 by the previous term. So you can kind of figure that out now. But I'm just going to keep working through the next two because we want the 6th term. So a sub 5 would be negative 2 times the previous term, which is a sub 4. So negative 2 times negative 24 gives us 48. And then the last one here, this is the one we wanted, would be negative 2 times a 6 minus 1, which is a to the 5th, or a sub 5. Negative 2 times 48 gives us negative 96. And that was the term we were looking for, negative 96. Okay, so let's try that again on 2B here. So on this one, we already know that A1 is equal to 8. I'll just switch colors here so we can get a little bit of change up here. So we already know that A1 is equal to 8. So I'm going to jump right to A sub 2, which now I can use this formula, which is 2A to the n minus 1. So 2A to the 2 minus 1, because n is 2 in this case, minus 7, right? All right, so going with that, I know that 2 minus 1 is 1, so A sub 1 is 8, so I'm going to plug that in here. So it'll be 2 times 8 minus 7, which is equal to 9. So I can go to the next term, A sub 3, 2 times what happened there? 2 times A 3 minus 1 minus 7. So it's going to be 2 times 9. We're using that. Minus 7. So 18 minus 7 is 11. A to the 4th. It's going to be 2 times A to the 4 minus 1 minus 7. So that's going to be 2 times that previous term here, 11 minus 7. So that's going to be 22 minus 7 is 15. Okay, keeping going over here. 2 more terms, right? A to the 5th is going to be 2 times A to the 4 minus 1 minus 7. So 2 times the previous term, basically, 15. So 30 minus 7 is 23. And so you're kind of getting the hang of that now. 2 to the A, 5 minus 1 minus 7 equals, 6 minus 1 here. This will be the 5th term. 2 times 23 minus 7, which is going to give us our 6th term to be 39. Okay, so a lot of work to those, but it's just kind of repeating the same thing, using that recursive formula to get the previous term before it, plug it in the formula, and go. Okay, another term, another common term we see a lot is a Fibonacci sequence. Okay, it's a common one. A lot of times we see it in nature, and so the example we're going to do has nature. It's often defined recursively. So this example here, suppose you've got a plant, starts to grow, the stem has to grow for 2 months before it's strong enough to support branches. So think of a tree, for example. At the end of the 2nd month, it sprouts a new branch, and it'll continue to sprout 1 new branch every month. So after 2 months, it starts to grow a branch every month, basically. New branches also do the same thing. They all have to grow for 2 months, and then they start a new branch every month. So if this pattern continues, how many branches will the plant have after 10 months? So we can look at the following table, and that'll tell us here that after 10 months, we've got 55 branches here, right? Because after the 1st month, you just have the 1 stem, nothing happened. After 2 months, you still have just the 1. But here's the thing, after the 3rd month, you start getting a new branch every time. And each of those also, so the number of branches kind of goes up recursively a little bit. So here's the table, and then we've got the term here, and it gives us this, we can kind of look and see that each term is the sum of the previous 2 terms, right? If you look here closely, you've got 1 plus 1 equals 2, and then here 1 plus 2 equals 3, and then 2 plus 3 equals 5. 5 plus 8 equals 5 plus 3 equals 8. So kind of that's what the Fibonacci is. Fibonacci is basically the next term. Each term is the sum of the previous 2 terms. Okay, so we can write that recursively like this. Now notice that sometimes, because we have this, we start with an A sub 0 sometimes, because it's going to be 1, and A sub 1 is also going to be 1. So sometimes, just be careful of that. Sometimes they start with an A sub 0. Okay, so looking at this, how many branches will a plant like the one described above have after 15 months? So if you think about 15 months now, let's use green since we're talking about plants. So after 15 months here, what will happen? So if I look at using this same idea, well, basically what I want is A sub 15. That's what I want to have. which is going to be, I'm going to need, since it's the sum of the previous two terms, I kind of need a 13 plus a 14, okay? Those are what I really need, but I don't have those yet. So I can figure those out, though, by just kind of finding some of them. Now I have all these, right? I already have that for us. I have the table, so I can start kind of at A11 here and say I know that's going to be the previous two terms, right? It's going to be 34 plus 55. So that's going to give us 89 branches after the 11th month. How about after the 12th? So now it's going to be these two added up, 55, 89 plus 55, which is going to be 144. And then the 13th, this is what we really want. After the 13th month, I'm going to add these two up, so I'm going to get 233. And then the 14th month is going to be kind of this and this added up, so it'll be 377. So that's kind of what I was looking for those two. Now I can kind of take these and say 233 plus 377 would give us a total of 610 branches after the 15th month. Okay, just kind of using that sequence as it is. All right, last thing here, and then we'll be done. So in this lesson, way back in lesson 1.3, back in chapter 1, we said that we looked at end behavior of graphs, looking at limits, right? We learned that if some functions, if they approach infinity, then their ranges approach a unique number, and we called that a limit. It wouldn't quite go to 0. It would come closer. It wouldn't quite go to, it wouldn't touch it, right? So we look at those as limits. As a function, an infinite sequence may also have a limit. So if we find out that the sequence has a limit, such as like they approach that unique number, right, then it's said to converge. And then if not, we say it is to diverge, okay? So let's just look at these. So the easiest way to do these is just kind of graph a few points here. So you've got a sub n. So if I look at this as the a sub n here, and then this is our n values. All right, so if we look at kind of these points, just kind of do it quickly here. Whatever we plug in for n, 1, 2, 3, 4, 5, 6, and so on. When we do this, we plug in 1 in here. Okay, you're going to get 64 divided by 2 is going to be 32. It's going to be way up here. Okay, then for 2, it would be 64 divided by 4, 16. So kind of down here, right? And then 3, 64 divided by 6 is going to be like 10 point something, 10.6. 4, 64 divided by 4, you can kind of see it's going to start doing this. When we get to like 64 divided by, when n is 6, it'd be 64 divided by 8, which would be 8, and starting to level off, right? But what's going to happen as we keep doing this is that the points are going to keep, as we keep going on n, they're going to keep going like this. Well, that kind of makes this little graph something like this. If we look at the n behavior, it's getting closer and closer to 0, but it's never going to quite get to 0. So this would be convergent. Because we can see it kind of has a limit approaching a certain number. Okay, how about this one? If we go here, a sub n is here, our n value is here. We look at 1, we know it's already at 9. Okay, we'll put it there. And then here's our sequence, n minus 1. So if I go there, a plus 4. Okay, so this is kind of the recursive one. So if I look at 2, it's going to be the previous term, 9 plus 4. Well, 9 plus 4 is 13, so it's going to go up here, 13. And then we're going to kind of keep doing that. It's going to be 13 plus 4 is 17. And then 17 plus 4 is 21 for each of these numbers, right? They're going to keep going up. And you can kind of see that this thing is going to eventually go further and further up. So it's going to, end behavior is going to approach affinity there. So this would also be convergent. And then the last one here, we can look at this one. If we just kind of sketch, and it doesn't have to be crazy, just have to be a little sketch to kind of get the idea, a sub n and n. And this one, If we look at our n values, 1, if I plug 1 in here, -1 to the first power is -1 times 3 is going to be -3. I got to draw a graph down here, right? -3. If we plug in 2, it's going to change it though, right? 2, -1 squared is going to be +1 times 3 is going to be 3 here. Okay. And if I look at the next one, 3, it's going to be -1 cubed is going to be -1 times 3 is going to take me down here to -3. And then so on. You're starting to see the pattern. If I go to the fourth power, every time it's even power, it's going to make that positive times 3. A +1 times 3 is 3. And then it's always going to be negative. So you kind of have this negative positive rotation here. So in this case, we say this is not approaching a limit. This is not approaching a certain number. This would be divergent. Okay. All right. So that's it for 10-1A. Not too bad. And if you have questions, bring them along with you.